right, welcome in. So let's go ahead and look at universal gravitation and basically what holds the entire universe together. And as the name gives out, there's a such thing called universal gravitation. We're going to find out how things are attracted to each other, what causes things to stay in orbit, and obviously not collide with each other. Not to say that it's impossible, but you know. Okay, so before we start with anything, we are going to watch a video by Mr. Anderson from Bozeman Science. There's a couple of reasons for this. One, he's a great absolute resource. His channel's got over 1 million viewers or 1 million subscribers. I recommend you guys also subscribe to him. Two, the visualization and the way he describes things are great, and we can all learn from it. But if there's some things that I will kind of pause and emphasize on in order to kind of get the point across, because he teaches AP physics and but it is very usable for us. Now the first thing that you see in the right hand corner is the little equation. It looks similar to the equation I introduced to you earlier, that equation 15, but that's not it. That's a portion of it, and we'll see how this plays into that equation. And by the end of it, by the end of this video and by the end of the lecture, you'll see how it all clicks together. So just be aware of the tiny little difference between this and the actual force of gravitation equation, which is number 15 on your formula sheets.
Hi, it's Mr. Anderson, and this is AP Physics Essentials 25. It's on gravitational field strength, which is a measure of the gravitational force placed on an object that's in a gravitational field. And so you know that the moon orbits around the Earth and stays there because of this gravitational field. And so if we place it in orbit, watch how the force on those two objects remains constant. The gravitational field strength is the same. But if we were to play around with this PHET simulation, if we move the moon closer to the Earth, you can see the force is increasing. It has greater strength. And as we move it away, it becomes less. How?
All right, so let's go ahead and discuss that part. As we just saw, when he brought them closer to each other, meaning reducing the distance, the force between them increased. And as he moved them away further from each other, increasing the distance, the force between them decreased. So this is the gravitational field strength. And an easy way to think of it is to think about yourself and just life in general. You know, if you're attracted to someone, would you be sitting closer to them or would you be sitting further away from them? Pretty easy to think about that, because if you like someone, they're your friend, you want to be closer. So the closer you are in terms of the distance, the more attraction there is. If, however, you don't agree with someone and you don't want to be around them, then that means that you don't have as much attraction and you try to go ahead and further increase your distance. So that's one way where you can increase or decrease the gravitational field strength, is by the adjusting the radius or adjusting the distance.
How else could we change the gravitational field strength? Well, we could increase the mass of the moon. It's a greater force. We could increase the mass of the Earth as well, and there's going to be a greater gravitational field strength, and it's going to have catastrophic consequences when we put it in orbit.
All right, well, that scenario obviously is not really possible in terms of just magically increasing the mass of the Earth or moon and so on. But when we discuss objects, but the whole concept is, if an object has a greater mass, it's going to go ahead and have a greater gravitational field. So that's another way in which you can go ahead and increase or decrease gravitational field strength. And essentially, mass is directly related to gravitational field, meaning if one increases, the other increases, whereas distance is indirectly related or indirectly proportional, meaning, as we just saw, if you increased the distance, you reduced the gravitational field. If you decrease the distance, you increase the gravitational field. So that's indirectly proportional to each other. And we'll talk more about that. But here's how the gravitational field looks like. The key thing is you see all these arrows, they're all pointed inward, and that's because gravity is attractive and it is pulling things to itself.
And so remember, any object that has mass is going to generate a gravitational field. And those field lines are going to point to the center of that object. And so any object, and we'll just deal with spherical objects in AP Physics 1, is going to have a gravitational field that's going to become greater the closer we come to that object. And so if you want to calculate the gravitational field strength, this equation works. And it was developed by Sir Isaac Newton. And it really only has those two things that we saw in that video. It's the mass of the object, and then the radius, or the distance between that object and the point. Now you might say there's three things in this equation. The first one is a gravitational constant. We lots of times refer to that as big G. But the other two things that are going to affect the gravitational field strength are the mass of the object and then the radius, or the distance from the object. And so in this class, you should be able to calculate the gravitational field strength of an object or sitting on the surface of a really large object like the planet. And so gravitational field strength, this is our equation right here. There are three parts to it. And so if we're measuring the gravitational field strength at a point separated from that object, we need to know the mass of the object. We need to know the radius. And note this, that when we're looking at the radius, it's not from the surface of the object, it's from the center of mass of both objects. In this case, one is just a point. And then the last one is going to be the gravitational constant, or big G, and that's just 6.67 times 10 to the negative 11th. And then we got a bunch of units coming in after that. And so look.
All right, so all those values, well, mass and radius usually will be given to you, or you may have to solve for it. The capital G, remember, that's your constant. That's number 51 in your formula sheet. You don't have to memorize it. You just have to be able to remember to use it when you need to. Again, this still looks a little bit different than the equation you're seeing in equation 15, because equation 15 says Fg is equal to big G times M1 times M2 divided by R squared. So this is a small portion, and as we go through this video and this lecture overall, you'll see how that fits in, but also how this comes into play for acceleration due to gravity. And hopefully things will make a little bit more sense.
Let me give you an example problem. Let's say I want you to figure out the gravitational field strength of a baseball. You can imagine it's going to be really, really small. There's not much mass in it. But if you want to solve this problem, I haven't given you enough information. You need to know what's the mass of that object. It's 0.145 kilograms. And you also have to know how far away is it. Let's say it's 2.0 meters. So you maybe have forgotten what big G is, so we'll put that right up there. 6.67 times 10 to the negative 11th. And so you may want to pause the video right now and try to solve this problem. Or you could just watch me do it. I'm going to take those three values and I'm going to place them into my equation. So I'm taking the big G times the mass divided by the radius squared. And so when I solve that, I get a gravitational field strength, or a G, of 2.4 times 10 to the negative 12 newtons per kilogram. If we cancel out all those units, we've got newtons on the top, we've got kilograms on the top, but we've got kilograms squared on the bottom. So we're going to end up with 1 kilogram on the top, and then the meters squared are going to cancel out. And so that's going to be the gravitational field strength of the baseball. Incredibly small, but it's still there. Let's say we were to do this. Can you figure out the gravitational field strength of the Earth? So we're sitting on the surface of the Earth. Can you figure out what's the strength of that force pulling you or holding you on the planet? Well, again, you'd need two more things. We're going to need to know the mass of the Earth, and it's pretty massive, 5.97 times 10 to the 24th kilograms. And you also need to know how far are you from the center of the Earth? What's the radius of the Earth? And it's 6.37 times 10 to the 6th meters. And so to solve this problem, you're going to do the same exact thing. We're going to plug it into those equations, those values. And again, it's worth doing, but
all right, so one little key difference is, and this is what I emphasized in last class, was to get in the habit of start using parentheses. Now, obviously, he uses the units within his equations, and we don't, but the reason he does it is so that he can show you which ones cancel out and how you end up with the final units. For our class, you don't need to do that. You are basically given what the final units is because we provide you with that. So we just do straight up numbers. But the difference is, and the reason I have emphasized this in the past, is to make sure that you have parentheses, especially when you look at the one at the bottom for the radius. When we start dealing with some of these radiuses and the distances, they're going to be rather large, and they're going to have their own exponent because of the scientific notation. In this case, this is 6.37 times 10 to the 6 meters. and you still want to go ahead and square that because it's r squared. Whereas in the previous problem, where he did with the baseball, I believe, was just, he said the distance was 2, you know, technically, he still had a parentheses around it. So again, just for habit, to make sure you're not messing up on the math, just regardless of what it is, have a parentheses. I personally have a preference of having fully parentheses regarding each one. And by that, I mean for G, one for each mass, and so on. And you'll see this when I solve my own problems. But again, just make sure you're using parentheses, and don't forget that the R needs to be squared.
Before, the gravitational field strength is going to be 9.81 newtons per kilogram. And so that is going to be the gravitational field strength as we get close to the planet. Again, it's also numerically equal to the acceleration due to gravity on our planet. And you might say it's going to be the same everywhere on our planet, but it's not.
Okay. So now you've kind of basically noticed how we calculate acceleration due to gravity. We take the gravitational field strength, we take the constant big G, we multiply it with the mass of whatever planet we're trying to deal with, in this case Earth, and we also take the radius of it, and that's how we find the gravitational field strength, which is the equivalent of your acceleration due to gravity. So we've always given you, gravity or acceleration due to gravity as 9.8 meters per second squared. I've told you that in AP Physics, they require us to remember it as 9.81 meters per second squared, but this is how you calculate it. And now, in a few slides, you will also see how this little equation plays out into the bigger equation, but also how it plays out into the basic F equals ma.
If you look at the gravitational field strength on our planet, and this is a NASA image, it's going to vary depending on where you are. Because the Earth isn't consistent, it's not a consistent sphere with consistent density, it's going to have differences in latitude and therefore the distance from the center of the Earth. There's going to be geological differences, what the Earth is made up of, and so we can study the gravitational field strength in different areas, and it tells us a lot about what the Earth is actually made of. And so did you learn to calculate the gravitational?
All right, so if a problem ever asks you to find the gravitational field strength, then that's what you would use. It's just that little g is equal to capital G times m divided by r squared. More than likely, you will not see these kinds of problems. We'll just may ask you, what's the gravitational field as far as force of gravitation between two objects? So that's why we use equation 15. But this is how you would go about finding g, or essentially acceleration due to gravity, if you need to. But this plays into our bigger equation, which is what we're going to deal with, and the majority of the questions you're going to be seeing. So there's that. Let's go to. Okay, so this is our actual equation, and this is Newton's law of universal gravitation, equation number 15. Remember that I said if you're using equation 15, just remember to flip-flop the numbers, the 1 and 5, to make it a 51. Because you need to use constant number 51. Constant number 51 is that big G. You don't have to memorize it. It's on the back of your formula sheet. There's a table called constants, and that's the very first one you see. So 15 uses 51. The value for that is 6.67 times 10 to the negative 11. Make sure that you always, punch in that negative 11, because that's telling the calculator to go back to the left 11 spots and put 10 zeros before that first 6. Whereas if you just forget the negative 11, it's saying to go to the right and add a bunch of zeros. So there's a huge difference. Make sure you use the negative 11. Also, for those of you who have calculators on your own, and there might be the fancier calculators, they have the option to store values under certain keys. So if you've got one that's got different letters, you could assign letter G to be stored as 6.67 times 10 to the negative 11. And that basically cuts down your time of punch it in every single time. So if you start solving these problems, you can just punch in, hit G, and then move on with the rest of it, and it works just as fine. It won't work with our basic TI-30s, but it will work with any other fancier calculators that you may have. All right, so let's look at this equation. Fg obviously is your force of gravity, any force measured in newtons. The big G is the gravitational constant. Constant means that it doesn't change. It has its own specific value. You don't need to memorize it. Again, that's number 51. You also don't need to memorize the units, as you know, there's plenty of letters and squares there. Anytime you're looking for a unit of something, it's always next to it, next to the word in your formula sheet. So you don't have to memorize the units either. Just keep that in mind. Then you got M1 and M2. And like I discussed earlier in the previous class, that 1 and 2, the subscripts, are just for identification purposes. It's just telling you the mass of the first object and the mass of the second object. Just make sure that, just like anything else, mass needs to be in kilograms. So do a quick check when you see values. And then finally, we have R squared. Now the R is the center distance. That's why I've highlighted it and put it a little bigger. So put a star around it. It is the center to center distance, and we'll see what that means visually. And of course, the distance or any kind of length needs to be in meters. So if you're given something in kilometers or centimeters, make sure to convert. So just a couple of things to be aware of right there. All right, so what does the constant g mean? Well, besides the fact that constant is always the same, it's saying if you had an object with a mass of 1 kg and a second object with a mass of 1 kg as well, and they were both just 1 meter apart from the center of each other, then the force felt between them would be 6.67 times 10 to the negative 11. And in fact, we're going to see that through a PhET simulation by Mr. Anderson, and he'll show you how that works out. So the G is constant, and that applies everywhere. Again, that's just its own specific value, and that's number 51 in your formula sheet. So now let's look at how that earlier equation plays into this. We've got F equals ma. We've done this before. We saw that, we played around with the smaller portion of this equation where it said G is equal to G times M divided by R squared, and that became our acceleration of gravity. So if you look at this equation now, it starts to make a little bit more sense. Remember that F is your weight. Your weight, of course, in this case is Fg. Now, we've always said that your weight is your F normal, the upward force, and that's true. Remember that Fg is the force that is experienced coming downward, and when you touch a surface, you have F normal, and F normal is the supported weight or force that is exerted equal to your weight. So when you look at the equations, for number 9, it says weight, and it says Fg is equal to mass times gravity. And that's the same thing as saying mass times acceleration of gravity, which is what you see in the top left-hand corner. So if F is your weight in Fg, and M2 in this equation is your actual mass, and we've got M1 as the mass of the Earth and R as the radius of the Earth, then we can see how this plans out into F equals ma. So which part of this equation is actually your Ag? Well, that portion right there, what we saw earlier. Acceleration due to gravity is the constant of G times the mass of whatever planet we're talking about, in this case Earth, divided by the radius of it. So that's where Ag is calculated from. We've always told you to basically memorize the value as 9.8 meters per second squared, but now you know how to calculate it, and you can calculate for different planets if need be. So, you may not be really asked about that, but this is just a little tidbit just to make sure you understand how things are starting to click together and where they come from. So that first portion of G times M1 divided by R squared, that is all for planet Earth, and that's your acceleration due to gravity multiplied by your mass, the M2, that gives you your Fg, which is your weight. So nothing realistically new here. We're just explaining how you get that. All right, so this is the important part, and there's a bunch of words on the left-hand side, and as I go through the slides, those words are still going to be in the next slide. So if I switch the slide, don't feel like you missed something. They're still going to be there. The big key takeaway from this is the visualization that I need you to see. Earlier, I said there was a center to center distance. We said that's R, and that's what we're referring to, from the center of M1 to the center of M2. So R, sometimes it might be radius of a specific planet if you're literally standing on it, or if you're talking about two objects that are way further apart, becomes the center-center distance. So that's the better definition to remember that, because the center-center distance is the correct definition for this. So that's what it stands for. And you also notice that it says F1 and F2. So this is kind of like saying, if you remember Newton's third law, equal opposite reactions. And we said that object A, exerts a force on object B, and object B exerts an equal amount of force on object A. So even though on your formula on the left, you just see Fg, both F1 and F2 are equal to each other, and that's your Fg. So the two objects feel the same exact gravitational field and force of gravitation. So let's go ahead and just take the most basic example and see how this pans out. Let's pretend that my girlfriend and I are on a date, right? And obviously I'm M1 and she's M2. So, and that R that you see is the distance between us at a restaurant. We're sitting at a table across from each other. You could say that that's a date. In the event that something happened and we decided to switch seats, meaning that now M2 is on the left-hand side and M1 is on the right-hand side, it's still the same exact date. Same two objects, same distance, nothing's really changed. Yes, we changed positions, but it's still the same exact date and the same exact force of gravitation. It's the same amount of, attraction. Now, if let's just say that I wanted to become more attractive to her, well, there's a couple ways. According to this, I would have to gain more mass, right? If you increase the mass, as we just saw, there's theoretically more attraction, because more mass gives you more gravitational attraction. But let's just say that, that's not going to be possible for me just to do that while eating one course of dinner. Instead, what you can do is reduce the distance. So if we were to sit closer to each other, that would signify far more attraction. By reducing the distance, we get a bigger gravitational force. If, however, I said something and she didn't appreciate it, and she basically took the water and just spilled on my face and decided to walk away, by that point, she's increasing her distance away from me. And you don't need to have a physics degree to realize that that has basically diminished and lowered the gravitational field. So if you increase the distance, you are lowering the Fg. If you decrease the distance, you are increasing the Fg. And that's basically what inversely proportional is. When it talks about directly proportional, means that as the product of M1 and M2 increase, the Fg increases. If the product of M1 and M2 were to decrease, then the Fg would decrease. So that's what directly proportional and inversely proportional is. Directly proportional, when one goes up, the other goes up. If one goes down, the other goes down. In this case, we're talking about if the product of the masses go up, then the Fg goes up, and vice versa. If, like I said, if the distance between the two objects, the center-center distance, is inversely proportional. So if one goes down, then the other goes up, meaning that as you reduced the center-center distance, then the Fg has increased. If, however, you increase the center-center distance, like I said, she just decided to walk out of the restaurant and keeps getting further away, and now you have decreased the Fg. So that's what inversely proportional is. Just be aware of potentially the definition, but also the concept, more importantly, the concept of how it works out. Now, you don't need to sit there and memorize it, because I've showed you methods on how you could easily solve for these scenarios. So if a question says, hey, what happens if you increase the distance? And if you forgot, remember that you have your original versus new method, and you could easily sit there and calculate that in about 15 seconds and get your answer. So you don't need to memorize. There's always a way to quantify things, and that's the beauty of physics. You basically have math that proves, things. So we'll touch base on those methods again, and in fact, those problems are going to come heavy going forward. So both for circular motion and both for gravitational and potentially anything else going forward. So I highly suggest that you also go back to my previous video where I covered those 5 sample problems step by step for logic problems under circular motion. All right, so we've tried to do this in the past. Obviously, we didn't have the correct spandex. It wasn't stretchy enough. And right now, it is not safe to do so with having people close to each other or trying to hold them. So we're going to go ahead and watch a little video on gravity visualized. And this will make more sense as of how different masses affect each other, how, different objects, mass, and all that stuff come into play.
Relativity, the explanation for gravity is that matter bends space. And so you put mass in a place in space, it warps space-time, and objects are not feeling a force of gravity, they're just following the natural curvature. And so this is a sheet of Lycra. Where do you get this? This is my old white shorts. No, there's literally a spandex.com. You can get a sheet like this if you buy the sale stuff, so you don't care what it looks like, right? For like $20, maybe less, depending on the sale. And so you put matter, and it warps space-time. And so if I have another object, it also warps space-time.
Okay, I'm gonna go off on a tangent, but does it not bother anyone that just random people are trying to, test the quality or to feel the spandex?
They feel that, and they're attracted to each other. And so that's Einstein's picture of gravity. Objects warp space-time, feel that curvature, and move accordingly. And if you have more mass,
Right there.
if you have more mass, it's going to bend space-time more. And so if you have objects here, they're going to respond to that, right? And so you put something there, now it's attracted. Now, in reality, that big mass would feel the warping of space-time by the marble too, right? It would move a little bit. We usually ignore that. The Earth makes the sun move a little bit, but it's so small you can ignore it. The moon makes the Earth kind of wobble around a point 3/4 of the way from the center of the Earth. We usually don't account for that when we're looking at satellite motion. Well, instead of just letting go of one, what if I give it a sideways push?
Okay, so he just mentioned something and said we don't account for that. Well, we're going to see a visualization of what he's referring to. I'm going to play that again. This won't be coming up on a test or anything, but it's just a good little knowledge just to be aware of, where different objects still have a gravitational field. They still play very little movement, but sometimes it's negligible, even though it might seem like it's a very large number.
We usually don't account for that when we're looking at satellite motion. You can ignore it. The moon makes the Earth kind of wobble around a point 3/4 of the way from the center of the Earth. We usually don't account for that when we're looking at satellite motion. Well, instead of just letting go of one, what if I give it a sideways push? Now it orbits. Now it's losing energy, which wouldn't happen in the solar system, right? Not noticeably. There's some perturbations on other planets and things, but this one does lose energy and spirals in. If I don't push it as hard, it will do an ellipse for a while anyway. And over here. So one of the things I thought of to do with this is when you study the solar system, all the planets are going around the sun the same way. Why is that? Why is everything going in the same direction? Well, the answer is it wasn't. directions. But there was a preferred direction. The disk it formed from had a slight preference one way versus another, and things going the opposite way got eliminated, and when it's all said and done, everything's going the same way. That works 90% of the time.
All right, so that's basically gravity visualized, and it's kind of what it's referring to. Object in space basically bends time, and that's what I call about time and space, and they get attracted to each other as a result. And the reason why many things don't collide is because they feel different gravitational pulls from different objects out in space as well. So it helps them to be able to keep in orbit. So this is what I was referring to earlier, or what he mentioned, and that it's negligible, but Earth moves up to 5,000 kilometers away from the common center of between Earth and Moon. And this is, of course, because of Moon's gravitational influence. So the Moon still influences the Earth, just not as much as the other way around, but it still causes the Earth to move. And as you look at the very top, it says currently it is 4,878 kilometers, and it kind of ranges from about 4,300 to about 4,900, 5,000 as time goes by. So again, not going to be on any kind of test, but just good to have for visualizations. Long story short, the Earth doesn't just stand still in its regular rotation. It's actually also being influenced because of the Moon as well. Okay, so now we get to our actual problems, and now you see the F1 equals F2. That's what I meant by that. When we solve for FG, both objects feel the same exact FG. So it's kind of like, if my girlfriend and I go on a date, regardless of how the table setting is, regardless if we're sitting next to each other or across from each other, or if I'm on one side and she's on the other side and we flip-flop, it's still the same exact date. So it doesn't matter where you're sitting at. What does matter is, the distance apart and obviously the masses. But the forces felt is still the same.
Hi, it's Mr. Anderson, and this is AP Physics Essentials video 45. It's on calculating the gravitational force. We all know that there's a force of gravity holding us to the planet, but an easy question might be, why don't you experience that when you're in space? Why are you weightless? Some students will tell me it's because there's no gravity there, but we know that's true because the moon is held around the Earth and we're held around the sun. There's got to be gravity out there. And so Newton explained this years ago. And so think about it like this. Imagine that we've got the Earth and we build a giant mountain on it, and then we put a cannon at the top of that mountain. And we launch a cannonball out at the horizontal. What's going to happen? Well, it's going to fall to Earth. There's a gravitational force between the cannonball and the Earth, and so it's going to follow this nice path. Let's say we launch it faster. What's going to happen? It's still going to fall to Earth. We still have that force towards the center of both objects. Let's say we launch it faster. It's still going to fall.
All right, so these three launches are basically what you first saw with that spandex video, is when he just kind of let it go straight and it went straight towards the object in the middle of that spandex. But once he said, what if I actually give it enough speed and it kind of rotated, you saw it go in orbit, is what you're going to see next.
To Earth, but if we launch it fast enough, what's going to happen? It's going to fall towards Earth, but it just keeps missing it. And so it's going to orbit around the Earth. This is how satellites work, and Newton predicted this years ago. And so what would it feel like to be inside that cannonball? Well, you would feel weightless. It's not that there's no gravitational force there. It's just as big as it was before. It's just that as you fall towards the Earth, you keep missing it. And so, again, Newton's law of universal gravitation allows us to not only understand this, but to quantify it, to come up with a value for that. We're going to do that in this video. So if we have two masses, there's going to be a gravitational force between the two, and that's always going to be attractive with anything in mass. Let's just assume that these are spherically symmetrical objects. The equation is really, really simple. It's simply the force is equal to big G, and we'll get to that in a second, times the mass of the two objects divided by the square of of the distance between the two. So you simply calculate the force by multiplying the masses times this constant, and then you divide it by the center-center distance, but you're going to square that value. Center-center distance is always going to go to the center of those two objects.
Okay, so key takeaways is that gravitational force is always attractive. You saw those with the arrows. We're going to see another slide where I emphasize this again. In the event that you come across a question, all arrows should be pointing towards whatever that object is. The other takeaway is the importance of center-center distance, and you see that being demonstrated at the very top. You may very well see a problem where they show you two masses and they'll say that right above that line is 5 meters. That's what they're referring to. So they may not always give you word problems. They might just say, you'll see the picture at the very top where it says mass, and the bigger one on the left, it'll say like 5 kg in it, and you'll see the mass on the right, and they'll probably say 3 kg in it, and then on that line at the top, it'll say like 8 meters. So that might be all you see in the problem, but what that means is, you got two masses, one with a mass of 5 kg, one with a mass of 3 kg, and their center distance is 8 meters. And there's your full problem, which you can go ahead and solve. So these problems could come in a variety of ways, whether it's pictures like this or actual word problems. Just make sure that it's gravitational force, always attractive, and you are looking at the center distance.
Objects, or the center of mass. Now, on our planet, the Earth is so big in relation to us that this gravitational force, or this gravitational acceleration, we'll call it G, is essentially constant. Changes in our distance from the Earth are so small, and the mass is so big in relation to our mass, that it really doesn't change much over time. And so here's our equation. If we have two objects, then the force is going to be equal between the two, and it's explained using this equation right here, where G, we'll refer to it as big G, is a constant, and it's worth memorizing. It's 6.67 times 10 to the negative 11th.
Now it says it's worth memorizing. You don't need to. Again, that's number 51 in your constant table. On your formula sheet, everything's given to you. Just remember that when you're using equation 15, you are using constant number 51. And like I said earlier, make sure you put it as a negative 11 when punching it in. Make sure that if you have a calculator with the capability, you can store it in there. But also get in the habit of always putting each one in its own parentheses. And you'll see that when I start solving them.
And so what else do we have in this equation? It's the mass of the two objects and then the center distance. And there's another.
Okay, so this is important, and let me explain what we're looking at. A couple of things you want to look at is the top arrows. Right now they're just little black ones, and there's not very long. It just says force in M1 by M2, and the force in M2 by M1. So those are the forces that they are being, feeling. And you have mass number 1, you have mass number 2. So as he manipulates these masses and he shows you the values, pay attention to the vector arrows and pay attention to those numbers. And you'll see that they're always equal to each other because, like I said, Fg for two objects is going to be the same. It doesn't matter if one's a lot lighter and one's a lot heavier.
Nice PHET simulation that gets at that. So if I have two objects like this, and I increase the mass on one, you can see the force is increasing on both of them, and the force is always going to be equal. Now, if we show the values, you see that those numbers are incredibly small. But what happens as we move them close to each other? The force gets larger. As we move them apart, it gets smaller.
So again, that key concept that as you decrease the distance between the two, meaning the closer they are, there's more force, there's more attraction. The farther away you are, there's less force or less Fg.
We can start to do some actual analysis here. If we make both of their masses 1 to make the numbers easy, and then we move them 1 meter apart, you start to see that gravitational constant.
Okay, so now they're 1 kg each, and they're 1 meter apart. And so that, and we're not talking about the humans, we're talking about the masses, the blue and the red, they're 1 meter apart. And remember that if that's 1 for each one of those, and the distance is also 1, then you have that G is equal to your F. That G, of course, being the big G, which was 6.67 times 10 to the negative 11. That's how you see it right there in standard notation with all the zeros. So rather than punching all that in, we just put it in as a scientific notation.
Come out It's a really small value. What happens now if we increase the mass tenfold? So if I increase this to 10 kilograms, you can see the force increases by 10. What if I increase this mass by 10? We also see a tenfold increase.
So this goes back to directly proportional. As you increase the masses, the force is directly proportionate to that, so that increases in the same manner.
But it's not the same if we're looking at the distance. If I double that, we're not just cutting it in half, we're taking it in by a fourth, and that's because we're squaring that distance between the two. And
so in that one, you just notice that as you increase the distance, you are drastically reducing the FG because it's being squared. So, just the smallest little increase in distance will have drastic effects in decreasing the overall FG.
Fourth, and that's because we're squaring that distance between the two. And so if this is our equation, let me show you how to solve a simple problem. And this is what you might see in a physics class.
Okay, so go ahead and write that problem down. It's the most basic one that you might see. Calculate gravitational force between two objects. Each one is obviously 3 kg, and they are 2 meters apart. So you have all the information to solve for this. And remember that the problem itself doesn't give you constant G. You should be able to use it yourself. Hopefully you've written on your paper. If you haven't,
calculate the gravitational force between two 3.0 kilogram masses that are 2.0 meters apart. And so this is going to be, really small value, hopefully, when you get it.
So if you haven't written on your paper yet, that's your value for G. So now you have everything available for you to be able to punch in and to solve this problem. So go ahead and knock that out within the next minute or so. Okay, so let's go ahead and see if you set it up correctly and if you're in the right path. Some of you may have already have the answer already.
And so we know the gravitational constant is 6.67 times 10 to the negative 11th. I'm given the masses and the center distance, and so it's really easy to solve that. I've got my constant G, then I'm going to multiply my two masses on the top, and then divide that by my center distance squared. And so if I simplify that a little bit, my constant is here. What happened to these units? Well, you can see that I've got kilograms squared on the top, kilograms squared on the bottom here. So those cancel, meter squared on the bottom, meter squared on the top. And this is simply 9 divided by 4, which is 2.25. And so what's going to be my force? 1.5 times 10 to the negative 10th newtons. So it's incredibly small value.
All right, so again, he writes the units in order to explain where each unit gets crossed out with and how you end up with your final unit. So in case you were kind of confused, kg times kg for those three each becomes kg squared. And if you look on the left-hand side, it is, you got meters divided by kg squared. So you have a kg squared at the bottom, theoretically, and a kg squared at the top. So those two cancel out. And then we have a meter squared from the left-hand side, because that's within that parentheses, and a meter squared on the bottom-hand side with a 2. And those cancel out, so the only thing you're left with is an n. We don't expect you guys to, ever write these within the equation, because we just say that basically we provide you with the final units in your formula charts.
Let me give you a problem that I'd like you to answer. So calculate the gravitational force acting on me standing on the surface of the moon. And so if you're given a problem like this, what do you have to figure out? Well, the gravitational constant is going to be constant, so you already know that. But what else do you need to know? You need to know the mass of the moon and the mass of me. And so the mass of the moon is a really large number, and the mass of me is large, but not that large. What else do we need to know? The center distance. And that's going to be the distance from the center of the moon to the surface where I'm standing.
All right, so your problem is right there. I'm going to go ahead and pause it there, give you guys a chance to solve this one as well. I don't believe he actually shows the answer himself. I think he puts it in his description. What I'll do is, more than likely, I will also probably put this in the description when I put in the video. But you have everything that you need. You're calculating for gravitational force, which is that Fg. Of course, you don't see Fg really listed there, but it's either one of those F's, F1 or F2. And you are, solving for that. So you have the radius, you have the center distance, which is that r, you have the mass of the Earth, and you have Mr. Anderson's mass. So make sure to just kind of write that down and start solving through it. All right, so by now you should have found your answer, and I will put the answer in probably the description when I upload the video. But if you are looking at it in your standard notification, standard format, your answer should have been 126.30 newtons. Or if you're in scientific, it will say that it is basically 1.26 times 10 to the second. So 126.30 or 1.26 times 10 to the second, they're the same thing, just different way of writing it. If you didn't get those, because you may have messed up on either the parentheses or the exponents. And this is why these problems become really difficult. So when it comes to your test or quiz, you should be expecting more theoretical questions. And by that, I mean the logic questions, because the chances of you messing up on those is less. So not to say that these won't show up, but also be ready for seeing those questions as well. We're going to cover that in again too. We've done that before. So let's go ahead and move on. Okay, another big thing that I said earlier, gravitational forces are always attractive. So if you see a possible test question or whatever, and arrows are not pointing inwards, those are wrong. If you got arrows pointing in all kinds of different locations, those are wrong. So make sure that all arrows are pointing towards the center, because pretend that that is the planet Earth and it's attractive. So that's what it means. Okay, so let's do one typical problem, and we'll go through the different scenarios in this. As you write this in the next slide, you will still see the same problem. So if I switch between, don't worry. But the question is asking for what's the gravitational force of attraction between two asteroids in space, each with a mass of 50,000 kg, separated by a distance of 380,000 centimeters. So this is pretty simple. It's just asking you to find FG. Now the thing is, it only lists one mass, but it says each with a mass of 50,000 kg. So even though you only see one 50,000, masses are both 50,000 each. And then you finally have separated by a distance. Okay, so the reason why I wrote this question this way is to highlight a few different things, and this is part of it. Number one, the big thing that you see is the distance was in centimeters. So you got to make sure your distance is always in meters and convert. So 380,000 centimeters is 3,800 meters. And the way you get that is you either divide by 100, because there's 100 centimeters in 1 meter, or you move back the decimal from the end 2 spots to the left. So there's different ways to convert, but it's 3,800 meters is your actual center to center distance. But I've highlighted a different version, and that's the scientific notation. And the reason I've done this, and the reason I'm going to use this, is to illustrate the importance of using parentheses, but also because if you ever are given a problem where they said that the distance is such and such and it ends in times 10 to the second, some people forget the fact that there needs to be an additional square. So that's why you see the r squared on the right being, in lime green, and then the bottom corner of it, you see that lime green too. It's just to point that out, to make sure that you don't forget to square that distance. So nowhere in this problem did it ever mention big G. That's your responsibility to use it. Again, when you have to use equation 15, you use constant number 51. So now when they made this slide, they put G on, kind of in the middle. I'm not a fan of this. I would much rather for G to always be at the very top next to the M's. In fact, in your formula sheet, that's where it's at, because all of those should be multiplied all across at once. So just like we've done in previous examples, make sure that everything has its own parentheses. And, and by that I mean the G itself has its own parentheses, the mass has its own parentheses, the second one has its own parentheses, And you also see me with 2 additional parentheses. This is specifically important for those with the lower calculators that are not as advanced, because you want to tell the calculator, make sure all this gets multiplied out first before you go further and divide it by our radius. And of course, you want your center distance, the r, to also be squared. So that's why you see the 3.8 times 10 to the second in one parentheses, and then you get the squared for that portion, and you close the parentheses for that. I know it looks a little tedious and it looks like a lot of parentheses, but if you write it on paper and you just convert it on the same way in your calculator, it won't be you won't be missing a question. So the FG in this case will be 1.15 times 10 to the negative 6 newtons. You may not be in scientific mode, you might be in standard, and you'll see a bunch of zeros and then a 115. So if you want to convert, the method to that is to simply hit second DRG. Usually they're right next to each other in your calculator, depending on the calculator, and you select the scientific mode, and it switches that for you. So these are the type of problems you'll come across when they give you actual numbers. Now, let's be realistic and let's look at what you could be asked to solve for. You'll never be asked to solve for G because that's a constant. Somebody's already done that for you. Somebody's already found that value. So in a problem, you're never asked to solve for G. You're either going to be asked for finding FG, which is something like this, or finding the, one of the masses, or basically the R. So those are possibilities, either mass. Sometimes they might have the same exact mass, so that's a possibility, or you might be needing to find R. There's no, they're not any more difficult. For example, if you're looking at solving the center to center distance, how far something apart is, that means that they've given you the FG, and that means that they've given you both masses, and you have big G as well. So in order to solve for the distance, you go back to the same trick that the whatever's at the bottom, in this case R, or R squared essentially, switches places with the FG. So they do a quick flip-flop, and it becomes R squared is equal to G times M1 divided by times M2 divided by FG. And you just take the square root of that. So it's just basic algebraic manipulation, but that's also a possibility. Okay, so we know that there's a huge potential for a lot of these numbers going wrong, and that's because of human error, forgetting to square something, and that causes your answer to be off. So for your test quiz, be prepared to see more types of theoretical questions, and that's not to say that you will never see these, but just be aware that it could be an equal amount or it could be leaning more towards that. So let's go ahead and touch base on those theoretical questions and how you could solve them quite easily. Okay, so as a meteor moves from a distance of Earth, 16 Earth radii, to a distance of 2 Earth radii from the center of the Earth, magnitude of the gravitational force between the meteor and the Earth will increase by how much? All right, so we see some numbers. We don't really see some actual units. It's a little weird. You don't need to write the full question. Just basically say, moves from distance of 16 Earth radii to distance of 2 Earth radii, and mention that there is a meteor, and mention that there's Earth, and we're trying to figure out how much will the gravitational force will increase by. So they've given us some numbers, and you might be inclined to find exact values. Can you do that? Yes. Should you do that? No. And here's a couple of hints. Hint number one is it just basically said, how much will that increase by if this change was made? It changed from going from 16 to 2. Well, we know we're reducing the distance, so we know we're obviously increasing the FG. We just want to know by how much. So it's basically referring to a factor. Is it 10 times, 15 times, whatever? They also didn't give us real actual numbers. Okay, 16 Earth radii is just a made-up number. Sure, you can look up the radius of the Earth and multiply it by 16 and multiply it by that 2. You can also look up the mass of the Earth, But what really we don't have is the mass of meteor. So we can't really solve for this from an exact point of view. So again, this kind of goes back to, hey, it sounds complicated, but you're actually pretty much in luck. It's just a little different variation. Okay, so how do we solve this problem? It's similar to the way we do original versus new logic method questions. It's just a small variation. And I'm going to touch up on that original versus new after this example. And I highly recommend that you go back and watch the video that I have for that, solving 5 of those problems, so that you have a solid foundation over it. That's what we did last class as well. But this is the variation. And the variation is they gave us some kind of number, albeit some fake number with a radius. It's still not exactly realistic numbers or actual numbers. So in this case, just to avoid confusion, I'm just calling this scenario 1 versus scenario 2. I don't want to call it original versus new because that's a separate thing. So we're going to do scenario 1, scenario 2. In scenario 1, this is the one where it was originally had a distance of 16 Earth radii. So we wanted to find out what the FG at that point was. Now, I could sit there and try to get all my exact values, but I want to be able to do it quickly, efficiently, and give an exact accurate answer as of how much greater it is. So in that case, I'm not really given actual values, so I don't need to use the constant G, the 51, the actual value of it. So as you see, my G, I'm just using a 1. And then for my mass of the first object, it doesn't matter if it's Earth or if it's the meteor, one of those, well, definitely the meteor, I don't have an actual mass for it. So I'm going to set that to 1. And to make life easier on myself, I'm going to keep the mass of the Earth as 1. Again, this is purely a theoretical question when you think about it. The only difference is they just gave us an exact value for how far was the R. And they said it was 16 Earth radii. So in my scenario 1, I have to include that that is a 16, and I have to square that. So it becomes, when I solve for scenario 1, it's essentially 1 divided by 16 squared, and it's 1 over 256. Or when you punch it in a calculator, it's 0.0039 newtons. So the FG in the first scenario is 0.0039 newtons. It's a very small number. Again, you were at 16 Earth radii, and we're going to be changing that to 2 Earth radii, which means we are decreasing the distance. And if you decrease the distance, obviously it's going to be increasing the FG. We just want to know by a factor of how much. So we're going to jump into scenario 2, and we're going to call that the one with the 2 Earth radii. Again, same scenario. I'm not changing anything else other than what they advised me to do, which was the Earth radii. So my G, I'm still going to keep that as 1. My masses are both still going to keep 1. And my Earth radii now is a value of 2 as opposed to 16. That's the only change I made based on this problem. So now it's 1 divided by 2 squared, and it becomes, 1/4, or basically 0.25 newtons. So we went from 0.0039 at 16 Earth radii to 0.25 newtons at 2 Earth radii. So what exactly, or how much do we exactly increase it by? Well, you take your new value, the 0.25, and you divide it by whatever the original was, the 0.0039. And we find out that it increased by a value of roughly 64 times greater. So by reducing the distance by essentially a factor of 14, it essentially increased our FG for this theoretical scenario as about 64 times. And that's, a legitimate answer. You've given them a realistic value. So whatever the original would have been, the second scenario would have been 64 times greater. most of your questions are going to be the ones we've covered in the past, last class and before we break with UCM sample problems, what you saw in your quiz. Those are the original versus new method. So let's go ahead and touch up on that. So what was the difference between this last one and the original versus new method? Well, remember, when you do the original versus new, everything in the original is always set to 1. That's when they don't give us any values. So there is no starting value, no numbers whatsoever. You get to decide what's better than deciding that, set your original to 1. So now let's go back to a problem. And again, you are going to see probably plenty of these coming up. And we've done a couple of these. So be ready for these kind of scenarios. The question is, what happens to the force of gravity between two objects if the mass of one object is tripled and the distance between them is halved? So, no actual number. They just tell you it's a theoretical question. What's going to be the end result? You just have to solve it out. So let's look. There's the problem again. There's our equation. It's asking us for finding the force of gravity in the second scenario, and after we make those changes. So in the original, we're going to say everything was 1. That's how the original versus new method works. Original, everything's 1. Therefore, all those values on the right-hand side of the equation is still 1. When it comes to finding out the new value, all you got to do is basically, all right, what am I looking for? You're looking for force of gravity, so you write that variable, and then you just follow the basic instructions, and you just do as they tell you. It says if the mass of one object is tripled. Well, there's two masses. You can decide which one gets tripled. Just don't triple both of them. Just do one of them. In this case, I did the first mass, which is the second number that you see in red. So that became triple the original. Not changing the mass of the second one. And the question also said, what also happens if your distance between them is half? And that's that R. Originally, in our problem, that was a 1. Having that is a 0.5. So that's how you set that problem up. And you've got Fg is equal to 1 times 3 times 1, which is 3, divided by 0.5 squared. 0.5 squared becomes 0.25. So 3 divided by 0.25 gives you 12 newtons. So compared to the original, the new one is 12 times greater. So be ready for these kind of problems. Like I said, we did this review for this last class. I had you guys do a couple of these problems. These are more likely to show up because, as you've seen in previous ones, if you mess up on an exponent, you could be greatly wrong. So be ready to do quite a few of these problems when it comes up. I'm not saying that this is the only ones, but obviously don't neglect them. All right, moving on. So this is more of a little complicated problem. Now, there's two A's. The first A is a typical problem. The second one is a little bit more advanced. You will not be seeing that type of question on a quiz or a test at all, but it's just in case you want to go ahead and have a additional harder challenge. But the first A, calculate the magnitude of the gravitational force of attraction between Io and Jupiter. It's just essentially asking for Fg. So I'm going to go ahead and show you how to set both of these up. And for the first one, you use equation number 15. So it's the same one that we've been doing. Just make sure that you use the distance, the center to center distance between the two. And once you find the answer to the first A, the Fg, for the second A, you're going to have to go back and use equation 7. And that's basically the net force is equal to mass times acceleration. Well, we know the mass, that's the one that I've used in red. So we're going to use that mass. We found our F from Fg, and you're simply going to be solving for acceleration that is exerted by Jupiter. So that's how you do it. And in the next slide, you will see the answers for them. Now, again, these are the second one, definitely you will not be seeing on the test. The first one, it's possible, but more of your questions are going to be regarding those theoretical type problems. So make sure that you watch the video on that. I had one for circular motion, And I also showed you some over here as well. And finally, if you need additional resources, remember the Bozeman Science with Mr. Anderson, great channel, great instructor, and you've also got the physics classroom with anything that you may need. There you have it. Have a wonderful day, guys.